and welcome to the machine learning course. In this first lecture, I'm going to talk a bit about the way the course will work, so more formal aspects, and then we're going to jump right into machine learning, the basic concepts, and see what are the objectives of this course. So to do away with the formalities, first you have all the material that you need at the course site. So at this URL you will have the slides, the lecture notes, the recorded videos, so everything you need to study about the course. And the classes will be available, the lectures will be available before the scheduled time, and I will try to keep them at around 90 minutes. So I don't promise that I can do this every time, but the idea is that often you will have time to view the lectures at the scheduled hours. So Fridays from 4 p.m. onwards. If you want, you can view the lectures before that or at other time at your convenience. I will try to post them online a few days before Friday. At 5:30 p.m. Until 6 o'clock on Friday, so at the end of the block allocated for the lectures, we will have a discussion on a Zoom meeting. You will have the link available on Clip, and this will be for me to answer your questions, whatever you want to talk about the lectures and any questions you have. So I would advise you to try to view the lectures before the discussion. This will be the most useful scheme. Then we'll have the tutorials. Once a week you will have a tutorial class of 2 hours, and the idea of these tutorials is to help you with any questions or difficulties that you have on the exercises. On the course site you have one page for the tutorials where you have access to a PDF file with all the exercises, and you have the schedule for the different tutorials. Most tutorials will be in person. The P1 will be online. It's right after the lecture, so it will also be online, and it will be via a Hangout. I will provide the link on Clip also during next week. Note that tutorials only start from October 8th, so only at the end of next week, and then the following week. There will be some sessions reserved for questions for the tests and revisions and help with the assignments, but you have all of these specified on the class plan. So look up the pages on the course site and you'll see the plan for the classes. For the assessment, you will be assessed in 2 components. A theoretical component which will consist of 2 written tests or the final exam. The tests will be during the class period. The final exam will be after classes end. The exam will be scored in 2 independent parts, with each part corresponding to one of the tests. So at the time of the exam, you will have each grade from each test, even if your performance on the exam is worse. So you can, if you want, skip some part of the exam and just do the other, or in whatever combination that you want. If possible, the tests and exams will be online, but I'm not sure what the rules will be. So if it's not possible to do them online, they will be in person. But at this moment, I cannot tell you for sure what will happen. The practical component will consist of 2 assignments in groups of 2 students, preferably in the same class in the tutorial classes. If you cannot form a group with another student from your own class, you can form with students from different classes, but I would advise you to form groups with students of your own class so that you can do the work during the tutorial classes together. Groups should be formed by October 31st. I will post on the course site the instructions for this, but basically you must each send an email to this address indicating the number of your colleague and so confirm the formation of the group. But just we'll wait a few weeks for classes to start so that you meet each other and arrange for forming the groups, and then you can start sending the emails. All the assignment submissions and group formation and so on will be using this email address, and you must send everything here using your official FCT account. So this is how I can identify you. So you must send everything from your official email address. Also note that this address here is only for automated processing of groups, of assignment submissions and so on. So in general, I will not be reading your messages. So don't use this address for questions. If you have questions, contact me directly. You have my email address on Clip, so you can send your questions to me or to your tutors in the tutorial classes if you want. For the final grade, your final grade will be the simple average of these two components, the theoretical and the practical component, but you must have a minimum of 9.5 out of 20 in each of these components to obtain a passing grade. Also, if you already did the practical component previously from 2017 onwards, you should not enroll in any practical classes so that you retain the grade. Only enroll in the tutorials if you want to replace your old grade with the new one, and in that case you will lose the old grade and have to redo the assignments. The software that we're going to be using is Python with these libraries, a few others, but basically these are the most important ones. But what I recommend is that you use the Anaconda distribution. This is free and it comes with the libraries that we're going to use pre-installed. If you already have an installation of Python and you are familiar with Python, it's not a problem. You don't need to install these libraries. Just check whenever you're doing the tutorials and so on. If you need some extra library, just install it with pip or whatever installer you use. So this would be my recommendation for those of you who are starting to use Python now. If you have already something set up that you generally use, then don't worry about it, just install the libraries as necessary. To read and keep up with the subject matter, I will recommend most strongly this book by Bishop, Pattern Recognition and Machine Learning, and also the lecture notes which you have available on site. I will also occasionally refer to a few other books, some chapters, so if you want to find them online or something like that and read them, that would be great. But this one I think would be the most important one for most of the subject matter we will cover. Okay, so that's the formalities and how things will work. Now let's look at the subject itself, machine learning. The idea of machine learning, of having the computer learn something on its own, is not recent. So you have this notion, this field of study that aims to give computers this ability to learn from examples without someone explicitly programming, and this comes from the late 1950s. So this idea is actually quite old nowadays. A more formal definition of machine learning comes from Mitchell in 1997. So basically you can find this in this book. This is a classical book on machine learning. And the idea is that we can say that some program is learning if we have a performance measure and we note that we use this performance measure to measure the performance of the program at some particular task, and the program is learning if the performance improves as we give it more examples, as the program gains more experience. So this requires the definition of these concepts. The notion here of experience will be the program having access to data, to the examples we are giving to it. The task we need to define, what is the task we want the program to do, and we also need to have some performance measure. So we have some objective way of measuring the performance of the program at that task. And learning in this operational definition is increasing the performance as measured by that performance measure P. So this gives us an idea of how we can formulate a machine learning problem. We need to understand what the task is, what we want the computer to do. We need to be able to measure the performance, so we must have some value that we can see if it's increasing or decreasing. And we also need data. We need that data so that we can give the experience, so to speak, to the computer and for it to learn and to improve that performance. For example, we want to have an automated flight ticketing system where a person can telephone the system and ask to book flights or on given dates between cities and so on, and the system does that automatically. So the task would be here to identify the requests for flight information, tickets, for booking flights, and so on. The performance measure would be the percentage, for example, of correctly identified segments in the speech, and the data would be voice records of requests that are also annotated so that we can feed this information into the system in a way that the system knows what it should do in each case. For example, if the person is saying, please book me on, this should be labeled as a request to book a flight. Flight 21 is the identification for the number of the flight, and so forth. So this could be the data that we have. We have the voice records and the labels for the different segments. We have a performance measure. We want to measure how much or how many of these segments the system correctly identifies, and we have a task which is to correctly label the different segments as we present the voice records to the system. So we can think of different types of machine learning problems. They all have this same fundamental scheme. We have a task, a performance measure, and data to help the system improve at that task, but we can be doing things that are very different. For example, in regression problems, we are trying to predict some continuous variable. For example, predicting the sale price of houses based on where the house is located, the number of rooms, the total area, things like that. In classification problems, we want to predict in which class some example belongs to which class it belongs to. For example, separating spam emails from regular emails. We have also other kinds of tasks, grouping similar things together, clustering. In this case, it's a bit like classification, but we do not specify the classes before. We want the system itself to find the best groups for our examples. We may want to estimate distributions and densities and so on, estimate how things are associated together. For example, people who buy diapers probably also buy formula for babies and things like that. So there are many different types of problems. We are going to look at some of them during this course, but remember that they all have this basic structure. There is some task, some performance measure that we need to optimize, and the data that we will use to feed into the system so that it can improve its performance. Machine learning is related to other disciplines. We can think of philosophical issues about epistemology, about ethics, for example. Nowadays, it's really a big concern with the widespread application of machine learning. It also has some inspiration of neuroscience in things like neural networks and the very idea of learning. Mathematics, for example, for efficient computation, numerical methods, and so on. This is also very important because when we put these algorithms to run, they need to be able to process data in a useful time frame and give us the results that we want. So there are many sophisticated numerical methods behind the algorithms that we're going to look at, but mostly we will not cover these many other disciplines to which machine learning is related. We will mostly focus on these two. So for computer science, because not only are you going to use actual code and use the libraries, implement things, so you need to know how to program a bit, at least a basic working knowledge of Python for this course, but also because we are going to look at the algorithms, and so it's important to use the kind of computational reasoning that students from computer science have. So those of you who come from other areas may need to study a bit more or have a bit more effort on this part to keep up with the parts for the algorithms and the implementations. But we're also going to cover a lot of statistics and probability, because you can even think of machine learning as a sort of applied statistics using computers. So the way to understand how these algorithms work and why they are constructed as they are and so on requires understanding this basis of statistics and probability. So those of you who do not come from a more mathematical background will probably have to put a bit more effort on this part of the course. But this is basically what we're going to focus on: the computer science and the statistical aspects of machine learning. So what's the use of machine learning? Basically, the most important application of machine learning is to solve problems for which we do not have an explicit solution. For example, if we want to write a program that identifies handwritten digits, that knows that this is 9, this is a 6, 2, and so forth, it's very hard to write code that will take a bitmap and output the correct digit, because then we will have to write rules such as if this pixel is black and that pixel is white and so on, and there would be so many of these rules that we would be lost trying to write such code. So since we don't know how to specify an algorithm to distinguish between the different digits, we're going to use a machine learning system that will build an algorithm that can solve this. And it will do so with examples. We give different examples of what these digits should be, and the system will search, the learner will search from a large bag of possibilities and give us at the end a set of algebraic operations that would give us the result that we want. So in this case, it will do some kind of function or a composition of many functions that when we input the bitmap, it will output the digits that are handwritten there. So this is useful because in many cases we cannot understand the specific steps necessary for solving the problem, but it's also useful when we have large volumes of data, because the more data we have, the more reliable this approach becomes. It is easier to get good results when you have large volumes of data than when you have small amounts of data. So this is good for things like Google, Facebook, credit card operations, and so on. Nowadays, there are lots of contexts in which huge amounts of data are gathered. And it's also important when we have systems that need to respond quickly to changes. For example, with your Facebook feed, different people will have different weights for different kinds of posts that Facebook is giving them, and Facebook is always trying to optimize the amount of time people spend looking at those feeds. So it will have to adapt the algorithms for different people. Each person at the end will have its own personalized algorithm, its own specific set of parameters and functions that will determine what that person sees on Facebook. It's also, it may be necessary to respond to changing conditions. So if you have a system that detects credit card fraud, and the criminals that are trying to commit fraud find out that some techniques are no longer working, they will try to change their approach, use new techniques, and your system needs to respond quickly to that. And sometimes this would take too long if you had actual engineers rewriting the code. So you need something that rewrites the code automatically and creates new solutions for those. So basically, machine learning is good if we have the right amount of data, and it's especially useful when we either do not have the specific recipe to solve the problem, or we do not have the ability to solve the problem by hand quickly enough, or with a personalized manner, doing this for each of our clients or something like that. Okay, so let's see some basic concepts to think about machine learning and think about how these algorithms will work. First, the most fundamental concept perhaps is the hypothesis class, which is the set of possibilities from which we are going to pick one hypothesis, one algorithm, so to speak, in order to solve our problems. So for this, we need to assume something about the solution that we want. Let's say we want to separate the red group from the blue group here, and we consider as possibilities horizontal lines. So the hypothesis class would be the class of all the horizontal lines that we can draw here, and our algorithm would be compare the y coordinate to some parameter theta, and if y is smaller than theta, then we consider it to be a blue example. If not, we consider it to be a red example. Note that this check here, if we have, for example, theta equals to 0, this would be our algorithm. If the y coordinate is smaller than 0, it's blue. If it's larger than 0, it's red. We could write this as a simple program and solve this problem ourselves, separating red from blue. But in machine learning, what we want is to have some system that will build us this algorithm. We don't need to figure things out for ourselves. So we would have something that would search different values of theta, find a good one, for example 0, and then output the hypothesis chosen from all these possible set of horizontal lines, the one that works for separating red from blue. Apart from the hypothesis, we have this model here, and the model is a way of representing the hypothesis class. So the hypothesis class in this case would be the set of all horizontal lines, and one way we can do that to represent here would be this equation, where we have one parameter that we can change, and if y is smaller than that parameter, then we consider it to be on the blue class. So this would be a way to represent all these different possibilities. We could think of a different hypothesis class, for example, circles of radius 1, where we would have two parameters, theta 1 and theta 2. This would determine where the circle would be placed. And we consider something to be on the blue class if the distance to the center, or if it's inside this circle of radius 1. Now the hypothesis class is merely where we are going to put the circle. We can put it over on this side or here on this part, or whatever we want, just by changing these parameters theta 1 and theta 2. So basically the hypothesis class is the set of all hypotheses that we are considering. The model is a way to represent mathematically these hypotheses. So typically we're going to use parameters in order to represent, for example, in this way, we are representing the set of all circles of radius 1. To get any of those individual circles, we just need to specify the values for theta 1 and theta 2, and we specify one of these circles. The hypothesis is one element from the hypothesis class that we can obtain instantiating the model by giving it parameters. For example, if we put on this first model here theta 1 equal to 0, we obtain this specific line here, and so now we have this algorithm for determining where if an example is red or blue, because we compare it with the line, and if it's below the line it's blue, if it's above the line it's red. The same thing here, we could specify an instance of the hypothesis class by specifying these parameters, theta 1 and theta 2, and we will obtain a specific circle. So in this case, it would be centered at -1, -1. And so we would have another way of deciding if an example belongs to the blue class, which be to check if it's inside the circle. If it's inside the circle, it's a blue point. If it's not, it's a red point. So the goal would be to find the best hypothesis, the best instance of the hypothesis class, so that we have, at the end, our learner has learned and now it can perform the task as we wanted. One thing that we can see immediately here is that there is a strong bias in the definition of the hypothesis class. If I decide my hypothesis class is all the horizontal lines, then I can only divide the two sets using a horizontal line. If I choose circles, then I can only separate these sets of points using circles and so on. This is called inductive bias. What we assume from the start determines the hypothesis class, and this limits which hypothesis we can choose. We cannot get a hypothesis that is outside the hypothesis class that we considered, because we are searching for the best hypothesis inside the hypothesis class. Now, we may think at first that this is a bad idea, because if we assume that it must be a straight line or a circle, something like that, we are limiting what we can choose. That is true, but without this inductive bias, we cannot really do any extrapolation. We are going to see this in a bit more detail at the middle of the semester when we look at learning theory. But the idea here is that the main purpose often is to be able to infer something about data points that we do not yet know from those that we already know. So the idea, for example, the purpose of being able to distinguish red and blue points would not be to distinguish these points as we have them, because these ones we already know they are red or blue, but it would be to predict something about new points that appear. So in this case, if a new point appears here, our system would say it's going to be a blue point. If it appears over here, it's going to say it's a red point. But in order to do this, to go from what we know to what we still do not know and infer something new, we need inductive bias. We need to have some constraint on the kind of models on the kind of hypotheses that we're going to choose. So we'll see this a bit more detail at the middle of the semester, but from now I would leave you with this idea that how we define the hypothesis class constrains the hypothesis that we can choose, but this inductive bias is necessary in order so that we can extrapolate from the examples that we already know to something we would like to predict in the future. So let's see in a bit more detail the kinds of machine learning problems that we are going to consider. One type of problem is the unsupervised learning problems, where we don't have previously labeled data. We don't have a right answer that we can specify from the beginning, but we want the learner to find some structure in the data. So what we have is that we have these feature values that we're going to feed into the learner, and the learner is going to give us new feature values. One concrete example would be clustering images. In this case, the clustering was done both using the image itself, so color distributions, the pixels and so on, but also using the HTML tags associated with the images on the internet. And this was used to try to group similar things together. So we can think that our learner is receiving as input the HTML tags and the matrices of pixels from the images, and is outputting labels for different clusters, different groups of images. And here you can see that these images, which are visually similar, have been grouped together. These ones have been grouped together too. This may seem a bit strange at first, but it's easy to see that they are images of Pluto, which includes both the Disney character and the planet and some sci-fi things related to Pluto. Here you have other images that are clustered together based on the color distribution and so on. So what the learner is doing here is finding out how to group these examples together so that similar ones are grouped closer and different ones are separated. What counts as similar and different will now depend on what we specify, but this would be the output of the learner. It's going to give us some new features that are, for example, which group each image belongs to. For unsupervised learning is used to find structure in the data, to extract features, and is often used as a first step for other learning tasks. For example, for supervised learning, because it allows us to do pre-processing, visualization, clustering, and so on. When we have deep learning, we're not going to cover deep learning in this course, but in deep learning, usually we can think of these kinds of first tasks of feature extraction and so on as being done on some layers of the network, and then other layers specializing on other tasks, or even building networks that can do this kind of recoding of the data. So you can find unsupervised learning also both on its own, for example, for clustering, but also integrated as part of supervised learning solutions. In supervised learning, the big difference is that we have this split of our data. What we feed the learner with are just the features. This is what we can generally observe both on the examples we already gathered, but also on new examples in the future. But we also split this part with the target values. So suppose we're trying to predict the sell price of houses. We can start with a set of houses that were already sold, and we have features that we can generally observe in all houses: the location, the area, the number of rooms, and so on. And this would be what we're going to feed into the learner. But in our data set, we also have the prices for which the houses were sold. So this would be the target values our learner should output if it performed perfectly. Of course, it generally does not perform perfectly, so we can measure the error here, and this gives us an indication of the performance that we can feed back into the learner in order to improve its performance. So we're going to try to adjust the parameters here to minimize the error between the price the learner is predicting and the price we know that house was sold for. This would be a regression problem where we are trying to predict continuous values. In a classification problem, we are trying to separate our examples in different classes, but the idea would be the same. We have a data set for which we already have those labels. For example, we have emails that are classified as spam and emails that are classified as regular emails, and we feed the features, the email text in this case, into the learner. We check what the learner is predicting, and we compare that with what we know the answer should be. If there is an error, we force the learner to adjust to minimize the error. So this is the basic scheme for supervised learning. We need labeled training data, but with these labels, we can check if the learner is predicting the values correctly and adjust the parameters to improve the performance. One example would be face identification. We have a set of faces that we feed into the learner so it can learn what faces look like, and then we can use it on images so it scans the image and identifies where faces occur. Of course, here we can also see an example of problems that we have. All the faces that we gave the learner are oriented vertically, and if there is a face that is a bit slanted, a bit on the diagonal, then the learner cannot identify it as a face. So here we see this problem. We're going to look at this in more detail, but if the training data is not adequately representative of what we're going to apply our system to, then we're going to have these kinds of failures. Another type of learning problem is reinforcement learning. In this case, it's a bit similar to supervised learning in that we have some feedback from the decisions of the learner, but in this case, the feedback may be sporadic and delayed. For example, suppose that you have a system that is learning to drive a car, and we penalize it very much if it crashes against a tree. It will receive that feedback when it crashes, but it must then assign responsibility to previous decisions, because the problem may have occurred a few seconds before, when the system decided to turn away from the road, and then later on it hit the tree. The same thing can happen if the system is learning to play a game or things like that, in which it can lose the game in a given move, but the error, the mistake was done a few moves before that caused the game to be lost. So in these cases, we want to optimize some function that tells us how the system is performing. We have some feedback, but the feedback is indirect, and we need some different approaches to solve these kinds of problems. So another common problem that sometimes appears is when we have some labeled data, but not enough to solve everything like a supervised machine learning problem, but we also have lots of unlabeled data. So in this case, in semi-supervised learning, we can join the two approaches of unsupervised and supervised learning and try to complement each other to improve the results. In our course, we're going to focus on supervised learning and unsupervised learning. Later on next semester, there will be a course on deep learning, and then we will cover a bit of reinforcement learning. But for this machine learning course, we will cover these two parts. And we're going to start with supervised learning because it's easier to understand some basic notions with supervised learning. And then later in the semester, we will move on to unsupervised learning. So the objectives of this course are for you to understand these basic concepts of machine learning, how to apply it, what kinds of algorithms we have, and the solutions, especially with supervised and unsupervised learning. Have some experience using these techniques, so you're going to actually use these libraries in scikit-learn and solve some problems with machine learning. But also to understand the literature and the language of machine learning literature. And this will require understanding mathematical formulation. So if you read papers or textbooks on machine learning, you're going to come up a lot with the mathematical formula. So in this course, we're also going to focus a bit on that, not with the goal of memorizing the formulas, because that's not very useful, but with the goal of learning to read them and become familiarized, so that when you find formula in the literature, you don't get scared or blocked by that. So we're going to start with an introduction to machine learning and with supervised learning. We're going to look at regression and classification problems, and this will take about half of the semester. Then we're going to look at learning theory, because after you have a more intuitive notion of how things work in practice, it's easier to understand some of the theoretical aspects. So we're going to start with that in the middle of the semester instead of the beginning. And then at the end of the semester, we're going to look at unsupervised learning, mostly clustering, distribution estimations, and things like that. Okay, to sum up this first lecture, we saw this idea of machine learning as making the computer learn from data without our having to specify explicit rules for solving problems. And we saw these basic concepts: the hypothesis class, which delimits what hypothesis we can choose from; the model, which is an expression or a representation of the hypothesis class and what we generally use to instantiate hypotheses from those classes; and the hypothesis, which is each specific instance that we can choose. So basically, our problem can be conceived as searching through the hypothesis class for the best hypothesis to solve whatever task we want the program to do. We saw this idea of inductive biases, which comes from the fact that when we specify a hypothesis class, we are limiting the kind of hypothesis that we can consider, but this is important for learning in the context of extrapolating from what we already know, the examples we have, to some new instances that may appear. And we saw these different types of problems. So I recommend that you read the first chapter of Alpiden and Mitchell if you want this. This is a bit old, this book by now, but it's a classical and can give you some this overview of machine learning, and also sections 1 through 4 from Martin's book. Okay, thank you all for your attention. That's it for this lecture.